So it's the turn for Gabriela. I don't know if you are presenting, maybe?
Yes, I am. Hello, everybody. Okay.
Okay.
So I will try to share my screen as everybody was doing. Okay. Let's see. Okay, so can people see the screen?
Perfectly, Gabriela.
Okay, thank you very much, everybody. Thank you for being here today in these strange circumstances for everybody. So yeah, I am Gabriela Ochoa. I'm presenting this work. There's a slightly change in the title, as you can see. We want to sell this idea of search trajectory networks, or STNs. And this is a work collaborating with Katherine Malan and Christian Blum. Probably you know them. Katherine is in South Africa, and Christian is German from origin, but is now in Catalonia in Spain, near Barcelona. And I'm proud to say that this is a paper in which there is no students or research fellows, so we did it ourselves, so we can still do some hands-on research sometimes when we have the time. Okay, right, so I'm going to start with a bit of motivation. The idea is that there are too many meta-heuristics. In this plot here, from this book, we can see like the established meta-heuristics starting in the late 40s till the mid-90s. So this is the genealogy. So we can see here in blue the single point methods, local search, simulated annealing, taboo search. You probably recognize some of them. In red, we have the evolutionary approaches, evolutionary programming, evolutionary strategies, genetic algorithms, etc. But the problem is that more and more meta-heuristics are constantly proposed. There is nothing wrong with metaphors, but we have to be careful that probably you have heard the work of Kenneth Sorensen. There are a bit of abuse of metaphors, so there have been meta-heuristics created about bacteria, wolves, cats, cuckoos, etc. Gravity, lighting, clouds, many ideas have inspired meta-heuristics. This is a title of a journal paper from this year, for example. So the problem is, or the question is, I mean, when the metaphor is stripped away, is the search process of these new methods, of these new novel meta-heuristics, any different than the existing established methods? So this is the question we'd like to address with this network-based visualization approach. So as I mentioned at the beginning, we are calling it search trajectory network, or STNs. And it's a tool to analyze and visualize the behavior of, in principle, any meta-heuristic, not only population-based meta-heuristic. It can be applied to single point approaches, etc. So they are inspired in the idea of local optima networks. Maybe some of you have heard about local optima networks, but the nodes are now not restricted to be local optima, but they instead represent a given state of the search process. For example, in population-based approaches, this state can be the best solution in a population. And the edges represent sequence or progression between consecutive states in the search process. That's what we call it trajectories. We also propose a way of contrasting two algorithms in a single network by merging the trajectories of two algorithms. So you can see here that we have two colors. I will discuss this in more detail, but basically we have two algorithms and we record the trajectory of these two algorithms, and we can identify each of them with a different color of the edges and of the nodes. Okay, so a bit of introduction of graph and network. The previous talks already is using networks, so all of us have been using graph. A graph is nothing else. It's a mathematical object that we have a set of vertices and a set of vertices and a set of edges, sorry. The vertices are the elements or components of the system, and the edges are connections, relevant connections between them. So graph theory have been done for ages, and this is a visualization of regular graph for 2 nodes or 3 nodes or 4 nodes. They are regular in the sense that each node has the same degree or number of incident edges. So when we talk about networks are kind of data-driven instantiation of graphs. And when we talk about complex networks, we're talking about graphs that they have non-trivial topological features. They are not regular as regular graphs, but they are not also completely random. they are somewhere in between. They have some interesting structures and they evolve over time. So this is a visualization of complex network of the World Wide Web, for example. And the idea is that complex networks have become an important tool to study many, many types of complex systems, from biology to the physical world, social networks, etc. So our idea is to try to use networks to study search. A little bit about graph visualization or networks visualization. So as I said before, graphs in themselves are mathematical objects. They don't have a particular unique visual representation. So graph visualization is the art of choosing an appropriate representation that will highlight some interesting properties of the network, and it will also be aesthetically pleasing. So in this example that I am showing here is the same network. It's a particular graph called the Peterson graph. So this is the same graph, but visualized in 3 different ways. So this will be a random layout, and these are 2 other layouts that somehow are interesting because they reflect the structure of the network. So a random layout will not necessarily be interesting, but if we have different layouts, we can kind of understand and see visually some structure interesting aspects of the network. So the type of visualization tools that I have been using in local optima networks and now in search trajectory networks are these algorithms, which I'll call force-directed graph layout algorithms. And these algorithms are inspired in this idea of having particles, which are charged, electrical particles, and there is also spring between them, like we see here. So there is a simulation process of these forces, and the idea is to produce a 2D distribution of the nodes and edges. And when the vertices are evenly distributed, we minimize the number of crossings, and the edges lengths are more or less uniform. And we can see here those are 2 examples of well-known algorithms. Another thing about graph visualization is we can use colors for representing different characteristics or features of the nodes or the edges. Okay. Okay, so in this work in particular, we have been talking about continuous optimization. So we are using these well-known benchmark functions that have different features here. We use five of them of different characteristics and different difficulties. So the benchmark function is the first one is the quadric function, which is the simple of the function. Then we have the Shiftle function and Michalevic function. This is a multimodal function that have many, as you can see, many peaks. And this is, Michalevic is also multimodal, but it also have these plateaus or areas of equal fitness. The other functions we are using is the Solomon function. We have the equation here. Again, it's a multimodal function. In this case, it has what we call a single funnel. But it has, if we look at the Solomon function in more detail, the zooming function here, we can see that they have these ripples, or these areas of the same fitness. And the last function we use is also very complex. It has many, many peaks. As you can see here, it's very rugged, and it's called rana function. And you also have multiple funnels. Okay, so I mentioned that we were trying to compare the behavior of 2 population-based algorithms or continuous spaces. So we use differential evolution. Differential evolution is a well-known and powerful algorithm for continuous optimization. The key idea of these algorithms is that we have a vector and we have differences that we use vector differences as a perturbation operator. So the algorithm, in very general terms, solutions are attracted towards combination of 3 other solutions in the population, and we only accept move if the combination is better than the previous one. Particle swarm optimization, there is many variants. The key idea of these algorithms is that the simulation of social behaviors of flocks or swarms. In this particular version, the global best PSO, solutions are guided by their own best known position, but they also follow, there is a formula to determine the position of the particles, and they also follow the best solution found in the swarm, the best so far. And solution will move regardless of not is a better solution. So just to try to differentiate the 2 algorithms on the very high level, in terms of the portion of the search space that share information to generate new solutions. In differential evolution, there are 3 other individuals, whereas in PSO, in this particular variant, the entire population also has an input in generating new solutions because the solutions are attracted to the best globally, to the best so far. Okay. Some definitions, I mean, we said that the nodes in these networks are not local optima. There are positions in the search space. So we came with this definition of allocation. Allocation is a partition of the search space containing solutions with a predefined distance or neighborhood. And the nodes of the network will be this location corresponding, if we are dealing with population-based algorithm, to the best solution in the population at a given iteration. The trajectory will be the sequence of locations representing these best solutions. So the edges will be directed and connect 2 consecutive nodes or states in this trajectory. So that the STN, the search trajectory network, is then a directed graph where the nodes are the locations and the edges are these consecutive trajectories or hops between states. Okay, so a little bit about our experimental setup. We have 10 runs per algorithm, and we have a stopping criteria of 5,000 function evaluation. These the dimension of the function. Remember, we are dealing with continuous spaces, so we have different dimensions for these functions. So the states, in order to have not so crowded networks, we record the states at each D iterations. So trajectories are of the same length and 100 in length. Interestingly, in order to be able to record solutions or locations in the search space, we need 2 precision values. The precision for the fitness function, the fitness evaluation, which is relatively high, 10 to the power of -8. And then we also need a solution for the vectors themselves, for the genotype. So the solution precision is a parameter that we selected depending on the dimension and the particular function. But for example, let us say that the solution precision is 10 to the -1. So the idea is then that we partition the search space into equally sized parts or hypercubes. Let's consider this example. Let's assume we have a function with 5 dimensions, and this is the fitness value. And this is the 5 vectors representing the components of the solution. And then in order to convert or to map solutions to locations, we simply round. So this vector becomes this vector with a precision of 10 to the -1. And then what we do with the fitness, we give a high precision to the fitness, but you can imagine that there can be more than 1 solutions in our combined trajectories of the 2 algorithms. And then what we do is assign fitness to the minimum as a representative of the hypercube, the minimum fitness, because we are minimizing functions. Okay, right, so I'm gonna now present the results, visual results and some statistics one by one. Remember, we have 5 functions. So what we see here, remember we have 10 runs per algorithm, and we also have a color-coded representation of the algorithm. So the red is the PSO, so the nodes and the edges visited by PSO. These are the nodes and edges visited by DE. If we have points or locations that are visited by both algorithms, we painted them in green. And this is the yellow points are the start of the search process. Remember, we have 10 of them, and we are the 2 algorithms are starting from the same 10 initial solution. You can see the yellow point here indicating in the 3D version of the plot, the vertical dimension is the fitness. So we are minimizing, and the big, in this case, is a quadric function. So the global optimum is an unimodal function, is located at the bottom, you can see here. And the size of the node is representative of the incoming degree. So the more edges incoming into the node, the larger it is. So in this case, both algorithms reach the global optimum all the time. So 10 runs, 10% success rate. In this particular case, the path length, by path length is measured by the number of steps, the trajectories. is larger for differential evolution. So this is the quadric function. If you remember, this is how it looked. We can only, of course, visualize it in this way in 2 dimensions, but here we are dealing with a 10 dimensions problem. Okay, so now I'm going to go to the second function. The Sheffield function is a multimodal function that also have several funnels. So we can see here that, let's start by looking at the success rate. Differential evolution, which is the blue trajectories, is 100% success rate, whereas PSO have 50% success rate. So 5 of the runs of PSO didn't get into the global optima. You can see here, this is the start. If we can follow the trajectory, you can see that 3 of the PSO runs end up in this point here that we can see in the 3D plot. So we are painting in dark gray, by the way, I forgot to mention, those solutions which are at the end of the run, which are not the global optimum. So you can see that 3 of the runs get completely lost in here, some other runs end up here, whereas all the trajectories of differential evolution end up in the global optimum. And in this case, the trajectories of DE are shorter. You can see they're more direct, shortening in terms of the path length than compared to the PSO. This is how you remember how it looks if we only have 2 dimensions, but in this case, as we are visualizing here, 5 dimensions of the Sheffield function. Let's go now to Michalewicz. Remember, Michalewicz have this particularity of having some plateaus, which are very close to the global optimum. Again, here, differential evolution has higher success rate. 8 of the differential evolution runs ended up in the global optimum. One interesting observation here is this black dot, which is not the global optimum, but seems to be attracting many of the search trajectories. You can see here. So remember, the size of the node is proportional to the incoming degree or the incoming strength. You can see in green here, these are areas which are visited by both algorithms. So you can see here, for example, this trajectory of DE visit this location, but this trajectory of PSO also visits here. And many of the trajectories get trapped in which I think is one of the plateaus or the ripples of the Michalewicz function. But then differential evolution, you can see here, this thick edge here, the thickness of the width of the edges represent the frequency of this path. So many of the trajectories are able to escape this plateau, differential evolution, and go to the global optimum. Okay, sorry, this is Michalewicz. This is how Michalewicz looks. And would say that this dark node here is corresponding to these plateaus. Okay, the Solomon function. Here we are seeing that, again, differential evolution have higher success rate and shorter trajectories. And this is a bit crowded here. We can see that most of the trajectories are good at getting very close to the global optimum. So what we am showing here at the right is a zoom, but very close to the global optimum. So this area that we see here, I am zooming. So you can see that the green dots are those positions or locations that are traversed by both algorithms. And we can see that most trajectories, a larger number of blue trajectories end up in the global optimum here. So this is how Solomon looks. Again, has ripples or plateaus near the global optimum. And our final function is rana. Rana was the hardest function, at least for PSO. You can see here that PSO has a success rate of 0. None of the runs was able to reach the global optima. So you can see the PSO trajectories really going elsewhere, going to these other points. And they are much longer as well. The PSO trajectories wander around and they are not able to reach the global optima. Whereas most of the trajectories, 9 of 10 trajectories in very short steps manage to get to the global optima in this function. Okay, so this is how rana looks. Right, in order to conclude, in particular for this case study where we studied 2 evolutionary algorithms for continuous optimization, we found that, in particular, that the PSO that follows the global best is not very suited for the multiphonal rugged landscapes and the landscape with neutrality. Remember that this particular version of PSO uses information of the best FAR solution, may be a hindrance in this case when we have multiple funnels or very, very rugged functions or functions with neutrality. And the more general message from the talk is that we hope that these search trajectory networks offer a more general approach to model search and understanding the dynamic of different algorithms. In this particular study, we study population-based approach for continuous optimization, but we hope it can be applied to many other meta-heuristics or combinatorial optimization. We can also try to observe and quantify those portions of the search space that track the search process and also visualize them. Okay, thank you very much. That's me.
Well, thank you very much. Clapping hands, you can hear it. Thank you very much, Gabriela. Nice presentation. I think we might have the time for one question, maybe two questions. So, well, I leave to the audience actually to unmute the microphone.
Yes, Juanlo, I have one.
Okay, Iñaki, go ahead.
Okay, so Gabriela, thanks for the interesting talk as usual with you. Just one question, excuse me, because I missed some part of the presentation because of my duties at home, but is the software that you use for representing the solutions and the landscape available for, because I think it could be very interesting for studying. I make some studies with grammatical evolution and genetic programming, and it could be nice to compare.
Yes, to be fair, it's not available yet, but I should make it available. I mean, this is a bunch of scripts which are not very tidy to be shared at the moment, but it's just a matter of making them available. It's all done in R. I mean, of course, the idea is that you log the algorithm. You don't need to use the existing algorithm to track the process. So if the algorithm, whatever language it is, so you need to save, to put some logs in your algorithm, and that produces a text file. And then the text file is read by R scripts, and then I visualize using this iGraph library. So yes, but they are not available yet, yes. But they should be.
Yeah. Okay, thank you. We will talk
yes,
in the future.
Yes.
Thank you.
Thank you, Iñaki. Maybe one last question.
I have one if I can.
Yeah, could you talk louder maybe, or
yes,
get closer to the microphone?
Yes, this is a problem. I will talk very loud. I have a small question. I very much agree on the things that you said about metaphors and the Kenneth Sørensen paper, which I know very well. And a small question about that is, do you know if there's any suggestion for a common vocabulary that all of us can use for population-based algorithms? And a slightly more tougher question is, I've seen this, I really like this work and really like the insight that the networks provide. Do you have any ideas on like more discrete problems, because this is like topologically limited because of the benchmark functions, such as let's say a traveling salesman or a scheduling problem? Do you have any ideas on that?
Well, as I said, originally we were working more on on discrete optimization. All the work on local optima networks we have done. There is some on the TSP, there is some on the quadratic assignment problem. It's now recently that we are looking at the continuous spaces, but there is a body of work on local optima networks on discrete, and including the TSP that you mentioned. So I can share you some references on that. Regarding the first question, no, I have no clue if we can come up with a common language. I mean, as I said, I'm not against metaphors. Metaphors have been very good for us. It's just the abuse of them. And I guess there is the pressure that we all have to be novel. We have to invent new things. And the novelty sometimes, we have to be careful that it's not the same thing with a different name.
Yes, or even worse, that you have one paper with 4 different terms for one concept, and it becomes completely unreadable, So
yeah.
So I agree. Let's make it up the common language. Thank you.
Okay. Sorry if I overrun my time.
No, you did good. You did exactly good, actually. Well, we are four minutes ahead of time, so I think that's
Okay.
perfect, actually. And in any case, the next presenter is me. So, and I don't care, you know. So I don't care about my paper. I mean, I care about yours. So that's fine. So thank you very much, and clapping hands again. Was really nice presentation. Thank you so much.